All right, YouTube. I want to talk about how what I know is true because the math doesn't lie, and I want to show you the math. I want to show you how I figured out. I want to show you how I determined that what I figured out is correct because I used math to do it. I use math to do everything because that's how you figure this stuff out. So like, and you can do this. You can even do this yourself. It's not that difficult. It's not that difficult math. It just takes some paper and some time and a pencil, and something that is very straight. So you got a straight line. I have a big giant ruler here. So I talked about in my previous video, take two sundials and put them 50 meters apart, and that I got a 1 degree, the shadow pointed inward towards the sun at 1 degree, which it shouldn't do because NASA says it's 93 million miles away, and at that distance it should just make a 90-degree angle. It should just be squared off at a 90-degree angle because the angle is so shallow. But 1 degree isn't as shallow as it sounds. It's actually it intersect 1 degree intersects with itself not that far out. So like what you do is I drew out the experiment on paper. I drew out the 50 meters across a 2 degree span on a circle because I got 1 degree on both sides, so that makes 2 degrees across. That makes a 2 degree span. And you do this. I drew a big circle, sun in the center, and then see, you've got 1 degree, 5 degrees, and 10 degrees here. So what I measured was the 1 degree at 50 meters. 2 degree difference across 50 meters. It's the same thing. It makes a big triangle basically. Big skinny triangle. I did it at 1:40 p.m. in the northern hemisphere in the USA. So what you do, we're going to use this formula that finds circumference, 2 pi r. Circle is 360 degrees. Those are our guides. Those are our references, so that we know, because we know a circle is 360 degrees, and the formula 2 pi r here finds the circumference of a circle, which will help us. So, what we're looking for, actually, what we're looking for is this, but this isn't what we're found. This is what we're told should be found, because we're told the sun's 93 million miles away, and it should look like this at 50 meters. Two boards 50 meters across or 50 meters apart should make two 90-degree angles when perpendicular with the sun. But what I found was this, and this is a measured, what I'm showing you right here, this is measured 1 degree inward. So 1 degree inward looks something similar to this. It's probably not perfect, but it should look something kind of like this. And this is what was found. This is what we're told. This is what was found. So I did the math on it. Diagram. When you get 50 meters across a 2 degree span, we want to know how many times that 2 degrees goes into 360 degrees, because that's how big the circle is. That's how many degrees in a circle. So it goes 180 times. So that 50 meters represents the 2 degrees. So we want to know circumference.
This is essentially a 2 degree segment, so it's not a perfect circle. This isn't going to be completely accurate because it's working off of a 2 degree segment, kind of like the polygons on a in a video game. Like you know how it's not it doesn't make a perfect circle. It just has lines that make a circle. That's kind of how this method is working. So we got a 2 degree segment that is 50 meters long times 180 makes 9,000 meters circumference. That's a 9,000 meter circle. So we want to know diameter. We're trying to find the radius because the radius will give us the distance to the sun. 9,000 meter circle divided by pi gives us the diameter, which is 2,864 meters. Then you take that diameter and you divide it by 2, which will give you the radius, which is 1,432.39 meters, or 1.43 kilometers. So we'll check it. We'll use 2 pi r. There's our circle that we found, 9,000 meters. And here's the radius. So we'll take our radius, 2 pi r, 2 times pi times 1.43 equals 8.98495 meters. That's pretty close. That's really close. So we're really not that far off at all. Like so now to check this one. So the 2 pi r checked that answer. So now we want to check that 1 degree. So like this is another method to check it. You do it manually. You draw out the experiment manually. Blow it up a little bit more and draw it out manually. You take each one of these boxes represents 5 meters. So I've got a line here that represents 50 meters. This is 10 boxes wide. This line is 10 boxes wide. And this the black square is just the house. It's just to represent where the experiment was relative to the house, because I helped use the house. but you draw it out 50 meters, 10 boxes. Each box is 5 meters. And you draw it out and you make a 1 degree. You get a big straight line like this ruler laying here. You see my lines are very straight. That's what it's here to show. There's no trickery. These lines are very straight. They're as straight as I could humanly possibly make them, and they're still not perfect, but they're pretty freaking straight. But you draw it out 1 degree at a long distance, not a short distance, because if you draw it out longer, it'll be more accurate. And you just draw it out. You keep bringing it out as far as you can until the 2 lines meet. And remember, our radius came up to 1.43 kilometers. This came out to 1.35 kilometers. And I'll show you. Because this line here, here's the 1 kilometer mark. See, that's 200 boxes. That number there represents 200 boxes. And here's this number, that's 1,000 for 1,000 meters. 1 kilometer. The 200 boxes, by the way, is so that you can do this yourself and check me. Because we should come up to if we're using the same type of grid paper, we should come up to the same. We should come up to a very similar number of boxes, is what it should be. And you see, I made corrections right here where I couldn't get things to, so you cut out that box right there. But it looks like I came up to 268 boxes. That's what it got up to. You see 1 kilometer, and here's 1.1 kilometer. There's 1.2. Here's 1.3, and then 1.35 right there. 1.35 kilometers. Just short, just a little short of what the math said, which is probably my human error, because you can see here it probably came short, because you see it's not perfectly even on both sides here. So it's probably out to like 275 boxes or something like that. But this is what it looks like when you do it all on paper. When you map it out on paper, you can do this yourself. Take 2 sundials and put them 100 meters apart if you want to. You just need the laser to be able to see the other sundial. You just need to be able to line them up. But I chose 50 meters because of the way I did it. I kept setting them further and further apart. I had suspicions that if this experiment would work, the shadows would point inward. So I just kept setting them further and further apart until the shadows did point inward. And it only took 50 meters to get them to do that, which was the point. I was trying to find the shortest distance possible with that it would happen. And the shortest distance possible would make sense to be 1 degree. So do this yourself. I've got the formula right here. I'll show it to you again. These are the steps you take. And please, if you try this yourself, please post it, show me, tell me what happened, tell me what you got, tell me, like, is it the same for you? And like, it should be pretty close in the summertime. It should be really close. If it's not the summer solstice, it'll be really close overhead. And if it's not exactly the if it's not exactly the winter solstice, it'll be really far ahead, or really far away. I mean, it'll be during the summer it's closer to overhead, and then during the winter it's further out. That's why there are these. That's why I have this first measurement from the first experiment that I did at 1.08 kilometers. That's when it happened. But understand, this experiment was before this one. So it would make sense on a later date that it's further away. Please try this yourself. This matches up with the analemma. It matches up with positioning in the sky. It matches, and it does not match up with what NASA says. Please try it yourself. I've shown you the math. It's pretty simple. You don't even actually need the math. You just need to set up the sundials and see if they point inward. See if the shadows point inward. If they point inward, what NASA says is wrong. Tell me what happens. See you.